Hello my dear friends, welcome to my YouTube channel. Myself Dattu Patel, Assistant Professor from LJIT. Earlier lecture we are already discussed about the functions of two variables and limit and continuities of several variable functions. Today's session we are going to discuss about the first and higher order partial derivative. Let's see firstly definition of partial derivative. A partial derivative of a function of several variable is the ordinary derivative with respect to one variable. That means remaining all the variables are constant. Consider the function f of xy, then the first order partial derivative are given by f suffix x, or we can write del f by del x equal to limit delta x tends to 0 inside the bracket f of x plus delta x of y minus f of xy upon delta of x. Similarly, derivative of with respect to y, then we can write fy or del f by del y equal to limit delta y tends to 0 inside the bracket f of x comma y plus delta y minus f of xy by delta y. Here del indicate by the symbol of partial derivative, and whenever we derivative with respect to x, then here we write x plus delta x, and whenever we write derivative with respect to y, then here we write y plus delta y. Now let's see the geometric interpretation of the partial derivative. Let's see our equation z equal to f of xy represent as a surface. In this graphical representation, blue color indicate by the our surface, and C1 and C2 which is indicated by the our curve C1 and C2 which is cut from the vertically cut from the surfaces, and that is point P, where P indicated by the ABC which is lies on the surface. By fixing the y equal to V, then our curve C1 in the vertical plane, then y equal to B intersect the our surfaces. In other words, we can say that C1 is the trace of S in the plane y equal to B. Likewise that vertical plane x equal to A intersect the curve C2 in both the curve C1 and C2 which is passes through the point P which is shown in figure. Notice that the curve C1 is the graph of the function g of x equal to f of x comma b, so that the slope of t1 or slope of its tangent, that is indicated by the t1 at point P, is g dash of a equal to fx of ab. The graph of the function g of y equal to f of a comma y, so that the slope of its tangent, that is indicated by the t2 on the tangent of the curve C1, that is T1, and tangent of the curve C2, that is T2 at point P, that is g dash of b equal to f of y fy of AB. That means partial derivative of fx of AB and fy of AB can be interpreted as a geometrically as the slope of tangent lines as the curve C1 and C2 of the surfaces in the plane y equal to b and x equal to a. Let's see the one example based on definition of partial derivative. If the function f of xy equal to x square y plus xy square, then find the fx or del f by del x. Here f of xy equal to x square y plus xy square, then according to the definition of partial derivative of first order, del f by del x equal to limit delta x tends to 0 f of x plus delta x comma y minus f of xy upon delta x. Here derivative with respect to x, then here we write x plus delta x. If derivative with respect to y, then here we write x as it is and y plus delta y. Now here substituting the x plus delta x and y in our given function in x square y plus xy square, then it becomes limit delta x tends to 0 inside the bracket x plus delta x whole square into y plus x plus delta x into y square minus function as it is x square y plus xy square divided by delta x. Now expanding this term and simplify that term, that x square y and xy square which is cancel out, then remaining term becomes limit delta x tends to 0, 2x delta x into y plus delta x whole square into y plus delta x y square upon delta x. Here from the numerator delta x which is common and cancel out from the numerator and denominator, the remaining term becomes limit delta x tends to 0, 2xy plus delta x into y plus y square. Now substituting the delta x tends to 0, then it becomes 2xy plus y square. Similarly, you can find the derivative with respect to y, del f by del y, with the help of definition. It's homework, try yourself. Now, let's see the next upcoming topic, which is higher order partial derivative. Partial derivative of the higher order of the function u equal to f of xy are obtained by the first order partial derivative. Suppose we have the function u equal to f of xy, then the first order partial derivative, that is ux equal to del u by del x and uy equal to del u by del y. Now according to the second order derivative, then we can write uxx or u as a suffix xx, then we can also write del square u by del x square, or we can write del by del x of del u by del x. Similarly for the uyy, then we can write del square u by del y square, or we can write del by del y of del u by del y. Similarly we have the derivative with respect to x and y, means uxy or uyx. Then first uxy, then we can write del square u by del x del y, or del by del x del u by del y. Uyx, then del square u by del y into del x, or we can write del by del y into del u by del x. Similarly you can go for triple derivation, u triple x, uxxx, uxxy, and so on. Now let's see the one example based on the higher derivative terms. Find the values of del f by del x and del f by del y at particular point 4 and minus 5 for the function x square plus 3xy plus y minus 1. Also we can find second order derivative del square f by del x square, del square f by del y square, del square f by del x del y, or del square f by del y del x. Let's see the first our function, that is x square plus 3xy plus y minus 1. Now derivative of that function with respect to x, then we can write fx or del f by del x. Whenever we applying the derivative with respect to x, then y treated as a constant, then derivative of x square, that is 2x, derivative of 3xy, then y treated as a constant, then derivative of 3y as a constant, and derivative of x, that is 1, then we can write 3y. Here y minus 1, that is also constant, then you all are aware about the derivative constant, that is 0, then it becomes 2x plus 3y. Now substituting the point 4 minus 5, then x indicated by the 4 and y indicated by the minus 5, then we can write del f by del x, where 4 and minus 5, then it becomes 8 minus 15, that is minus 7. Similarly derivative of with respect to y, then here x, that is our constant, then derivative of x square, that is 0, and derivative of 3xy, that is 3x, and derivative of y, that is 1, and 1 as a constant, then it becomes 3x plus 1. Substituting the point means del f by del y where 4 and minus 5, then x as a 4 and y as a minus 5, then it becomes 12 plus 1 equal to 13. Now let's see the second order derivative, del square f by del x square, or we can write del by del x, del f by del x. You all are aware about the values of del f by del x, that is 2x plus 3y, then del by del x 2x plus 3y, then it becomes 2. Similarly del square f by del y square, then del by del y of del f by del y, substituting the values of del f by del y, that is 3x plus 1. Here 3x plus 1, that is constant, then derivative of constant, that is 0. Likewise z, we can find del square f by del x del y, then we can write del by del x of del f by del y, substituting the values of del f by del y, that is 3x plus 1. Now derivative of that particular term with respect to x, then it becomes 3. Similarly, del square f by del y del x, then we can write del by del y of del f by del x. Here, substituting the values of del f by del x, that is 2x plus 3y. Then derivative of this term, that is 3. Now let's see the one more example. U equal to e raised to 3xyz. Then prove that del cube u by del x del y del z equal to 3 plus 27xyz plus 27x square y square z square into e raised to 3xyz. Here the sum in form of prove that, or here that is the third order partial derivative. Then we start with firstly derivative with respect to z, del u by del z. Then whatever the answer of del u by del z and derivative of that particular term with respect to y, and whatever the answer, that is del square u by del y del z and derivative with respect to x, then we get del cube u by del x del y and del z. Then firstly we can write del cube u by del x del y del z equal to del by del x into del u by del y into del u by del z. Here u equal to e raised to 3xyz, then derivative of u with respect to z, then obviously derivative of e raised to x, that is e raised to x, then e raised to 3xyz, and derivative of 3xyz, that is 3xy. Then we can write e raised to 3xyz into 3xy. Now derivative of that particular term with respect to y, then we can write del square u by del y del z, or we can write del by del y of del u by del z equal to del by del y, substituting the values of del u by del z. Here 3x, that is constant, then comes out the remaining term e raised to 3xyz into y. Here derivative with respect to y, then that is apply the product rule, means u as it is derivative of v plus v as it is derivative of u. 3x, that is constant, inside the bracket e raised to 3xyz as it is derivative of y into 1 plus y as it is derivative of e raised to 3xyz, that is e raised to 3xyz into 3xz. Now simplified that term, means e raised to 3xyz common, remaining terms becomes 3x plus 9x square yz. Now derivative of that particular term with respect to x, then it becomes del cube u by del x del y del z, or we can write del by del x of del square u by del y del z, substituting the values of del square u by del y del z, then it becomes del by del x of e raised to 3xyz inside the bracket 3x plus 9x square yz. Again we have to apply the product rule. Then u as it is derivative of v plus v as it is derivative of u. Then here e raised to 3xyz as it is derivative of v means 3 plus 18xyz plus v as it is means 3x plus 9x square yz as it is derivative of e raised to x, that is e raised to 3xyz, and v derivative with respect to x, then into 3yz. Now in this particular term e raised to 3xyz common, then remaining term becomes 3 plus 18xyz plus 9xyz plus 27x square y square z square. Here in second and third term both are same, then addition of that particular term, then it becomes 3 plus 27xyz plus 27x square y square z square into e raised to 3xyz. That is our RHS portion. Hence prove that particular sum. Let's see the next topic, which is Clairaut theorem or mixed derivative theorem. If u equal to f of xy possesses continuous second order partial derivative uxy and uyx, then del square u by del y del x, which is same as del square u by del x del y, or we can write uxy equal to u of yx. Similarly, for the third order partial derivative f of xxy equal to f of xyx, which is same as f of yxx, and similarly f of xyy equal to f of yxy equal to f of x. Now let's see the one more example based on the Clairaut theorem. If z equal to x plus y raised to x, then prove that del square z by del x del y equal to del square z by del y del x. Firstly, z equal to x plus y raised to x, then partial derivative of first order with respect to x and with respect to y, that is del z by del x. If we derivative with respect to x, then y treated as a constant, then del z by del x equal to derivative of x, that is 1. Here y raised to x means y that is constant, then we can say that a raised to x, that is our exponential form. Then you all are aware about the derivative of a raised to x, that is a raised to x log y, then it becomes 1 plus y raised to x log y. Similarly, derivative with respect to y, then del z by del y equal to x, that is constant, then derivative of constant, that is 0. Here y raised to x, then we can say that derivative of x raised to n, that is n x raised to n minus 1. Then here x y raised to x minus 1. Now let's see the second order derivative, which is del square z by del x del y equal to del by del x del z by del y. Substituting the values of del z by del y, that is x y raised to x minus 1. Now substituting the partial derivative of that term with respect to x, then obviously here product rule, then u as it is derivative of v plus v as it is derivative of u, then it becomes y raised to x minus 1 plus x into y raised to x minus 1 into log y. In this term y raised to x minus 1, which is common, the remaining term becomes 1 plus x log y, that is our equation number 1. Similarly, del square z by del y del x, then we can write del by del y of del z by del x. Substituting the values of del z by del y, then it becomes del by del y inside the bracket 1 plus y raised to x log y. Here 1, that is constant, then derivative of constant, that is 0. Remaining term y raised to x log y with respect to y, then obviously product rule, u as it is derivative of v plus v as it is derivative of u, then it becomes y raised to x as it is derivative of log y, that is 1 upon y, plus log y as it is derivative of y raised to x, that is x into y raised to x minus 1. Then simplified that term, then it becomes y raised to x minus 1 plus log y into x into y raised to x minus 1. Then in this particular term, y raised to x minus 1, which is common, inside the bracket 1 plus x log y, that is equation number 2. Then according to the equation number 1 and 2, we can say that del square z by del x del y, which is same as del square z by del y del x. Now let's see the next upcoming topic, which is Laplace equation. Laplace equation is the function of two variables which is given by the del square f by del x square plus del square f by del y square equal to 0. Or we can say that if function u equal to f of xy, then del square u by del x square plus del square u by del y square equal to 0. And according to the three variables, then we can write del square f by del x square plus del square f by del y square plus del square f by del z square equal to 0. Suppose our Laplace equation in form of polar coordinates, then it's given by the del square f by del r square plus 1 upon r del f by del r plus 1 upon r square del square f by del theta square equal to 0. Let's see the one example based on the Laplace equation. Determine the whether u equal to ln square root of x square plus y square is a solution of the Laplace equation or not. In this particular example, we don't have the any conditions to the finding the del square u by del x square or del square u by del y square or whatever the condition was not given. But here show that Laplace equation is satisfied or not. Then you all are aware about the what is the Laplace equation for the two variables, that is del square f by del x square plus del square f by del y square equal to 0. Then here our function, that is u equal to f of xy equal to ln square root of x square plus y square. Then according to the properties of logarithm, u becomes 1/2 ln x square plus y square. Then firstly, partial derivative of u with respect to x and with respect to y, then obviously del u by del x equal to derivative of log, that is 1 upon x then we can write 1/2 1 upon x square plus y square, then again derivative of x square plus y square, that is 2x, and y square, that is constant, then derivative of y square, that is 0, then it becomes x upon x square plus y square. Likewise that we find the derivative of with respect to y, that is 1/2 into 2y upon x square plus y square. Here 2 which is cancel out, then remaining term becomes y upon x square plus y square. Let's see the finding the derivative of second order, means del square u by del x square equal to del by del x of del u by del x. Substituting the values of del u by del x, here in numerator and denominator portion both has a variable x, then obviously apply the quotient rule, means del by del x of u by v, then v as it is derivative of u minus u as it is derivative of v divided by v square. Then here it becomes x square plus y square into 1 minus x as it is derivative of denominator portion, that is 2x, upon square of denominator portion, that is x square plus y square whole square. Simplified the numerator portion, then it becomes y square minus x square upon x square plus y square whole square. Similarly, for the second derivative of with respect to y, means del square u by del y square equal to, we can write del by del y of del u by del y equal to del by del y of, substituting the values of del u by del y, that is y upon x square plus y square. Similarly, here also numerator and denominator portion has a y, then obviously quotient rule, then v as it is derivative of u minus u as it is derivative of v divided by v square, then it becomes x square minus y square upon x square plus y square whole square. Now according to the Laplace equation, that is del square u by del x square plus del square u by del y square, then substituting the values of del square u by del x square and del square u by del y square in denominator portion has the same value, then common taking LCM, then y square minus x square plus x square minus y square in numerator portion which is cancel out, then it becomes 0, or we can say that common minus sign in second term, then first term and second terms are become same which is cancel out, that is 0, then we can say that our function u of xy is a solution of Laplace equation functions. I hope you guys learned something from this video. If you think that this video will help some of your friends, then do this share with them. If you want to watch more videos like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. If you like this video, then thumbs up. If you have any query regarding this, then feel free contact me. Thank you so much for watching me.